Hey guys, welcome. Yeah, so problem 7 here, and what we have to do is find the interval of convergence, including endpoints of the series this. Now, um, partially because other than 42, 7 is my favorite number, and partially because problem 8, which is the final problem on this Calc 2 Ivy League midterm, is also another convergence question. I might actually conclude this video series on this problem, which is I'm not going to make a video on problem 8 unless, again, this video series catches on fire, because I feel like we've covered enough problems on convergence in this video series. All right. Anyway, to do the interval of convergence here, we have to do the ratio test. And so then we take an to be the inside of sigma, and an plus 1 is going to look like this. Now, note that here on x minus 1, the exponent is 2 times n plus 1 plus 1, and therefore it simplifies to 2n plus 2 plus 1, or 2n plus 3. And so then similarly, the denominator is going to be 2n plus 3 for a sub n plus 1, yeah? Otherwise, the ratio test says to take the limit of the absolute value of the quotient a sub n plus 1 divided by a sub n, and take the limit as n goes to infinity of that quotient, the absolute value of a sub n plus 1 over a sub n. And if that is less than 1, then we converge. And if it's greater than 1, we diverge. And if it's equal to 1, the test is inconclusive, right? Okay, well, we do interval of convergence, like I said, using the ratio test, and then taking this limit of a sub n plus 1 divided by a sub n in absolute value as n goes to infinity, and requiring that it be less than 1 is how we're going to find the interval of convergence. All right, so given our a sub n and our a sub n plus 1, a sub n plus 1 divided by a sub n is going to be a sub n plus 1 times the reciprocal of a sub n. So that's what I have here, and then we take the limit as n goes to infinity of the absolute value of this stuff, right? Okay, now there's a lot that simplifies inside that absolute value. The first of which is canceling this negative 1 to the n in the denominator with negative 1 to the n plus 1 in the numerator to get a negative 1 in the numerator. But since we have absolute values, we could just get rid of the negative 1 powers altogether. In other words, like after canceling denominator and numerator, we don't need to keep a negative 1 in the numerator because of the absolute values. Yeah, all right, cool. Otherwise, nothing else is done from this step to this step here. And so let's make some more progress in the next couple of steps. So here in this step, we bring the quantities involving just n and no x together here in this quotient, and then we bring together the quantities involving x, which is x minus 1 to the power 2n plus 3 divided by x minus 1 to the power 2n plus 1. Now, those two simplify to just x minus 1 to the second power in the numerator, and then otherwise we have these two guys still here, and in our next step we're going to give two separate absolute values, one to the quotient 2n plus 1 divided by 2n plus 3, and then the other to x minus 1 all squared. Okay, cool. Now the limit as n goes to infinity of this quotient right here is clearly 1, right? Okay, for large n, plus 1 and plus 3 make no contribution, really. They make negligible contribution for large n as n goes to infinity. And so then we're just looking at the quotient 2n divided by 2n then, and that's clearly 1. And so the limit as n goes to infinity of this is just going to be this here. Now what we said is we take the limit as n goes to infinity of the quotient, the absolute value of a sub n plus 1 over a sub n, and we require that it be less than 1 in order for it to converge based on the ratio test. So then that means we take this guy here at the very end after taking care of our limit as n goes to infinity, and we require that it be less than 1, which is what I've showed here at the bottom left. Now, this absolute value inequality will mean that we have x's from 0 to 2, right? So solving this absolute value inequality is going to give you the solution that 0 be less than x be less than 2. And therefore, for such x's, our series converges absolutely. Okay, and now we have to worry about the endpoints, namely 0 and 2. So what happens when x is 0 and what happens when x is 2? And of course, we're going to come back to the original series and replace this x here with a 0 first. Look at that, and then replace it with a 2, and look at that and make conclusions about the endpoint. So we need space to do that, so let's make space. Now, when x is equal to 0, we replace this x, like I said, with a 0, and that means we have this here, and that simplifies to this here. And why, you say? Because 0 minus 1 to the power 2n plus 1 is just negative 1 to the power 2n plus 1. But wait, right here we already have negative 1 to the power n. So we have negative 1 to the power n times negative 1 to the power 2n plus 1, and that makes negative 1 to the power n plus 2n plus 1, or negative 1 to the power 3n plus 1. All right, cool. Now we can simplify this a little bit more, because negative 1 to the power 3n plus 1 is like negative 1 to the power 3n times negative 1. But negative 1 to the power 3n is negative 1 cubed to the n, but negative 1 cubed is negative 1. So it's just negative 1 to the n, and then times negative 1 from the plus 1, as I said earlier, if you caught all that. And so basically this reduces to negative 1 to the power n plus 1. So in place of 3n plus 1, we can write n plus 1 as an exponent of negative 1 in the numerator here, is what I'm saying. Yeah? Okay, cool. If we do that, then I'd have to display this here. Now, this converges by the alternating series test. First of all, from the negative 1 to the power n plus 1, it's alternating. And then 1 over 2n plus 1 is decreasing. It's a decreasing sequence. In other words, 1 over 2n plus 1 is bigger than 1 over 2 times n plus 1 plus 1, right? So, in other words, in other words, a sub n plus 1 is smaller than a sub n if you take a sub n to be 1 over 2n plus 1, is what I am saying. So by the alternating, clearly the limit is n goes to infinity of that a sub n, which is 1 over 2n plus 1, is 0. So since all three requirements of the alternating series test are fulfilled by the alternating series test, we say that this series converges, meaning that the endpoint x equals 0 will be included in the interval of convergence. All right, what about x equals 2, the other endpoint? Well, there, our series is going to be this, right, when x is equal to 2. And then this is 2 minus 1, which is 1 to the power 2n plus 1. Well, we don't need to write that. So our series, when x equals 2, reduces to this here. And for the same reason as this other guy here, this here is going to converge, which is the alternating series test. It's alternating, it's decreasing, and the limit is n goes to infinity of 1 over 2n plus 1 is 0. So all three requirements of the alternating series test are fulfilled. So it converges. Therefore, the interval of convergence is 0, 2, including the endpoints 0 and 2. And this is an interval notation, right? Which is saying 0 is less or equal to x is less or equal to 2. Yeah? Okay, cool. All right, this is it for this Calc 2 Ivy League midterm. I hope you enjoyed it. But otherwise, yeah, take care.